very soon we'll arrive at the decay equation. When I talk about this decay, so-called carbon nuclei decay, actually I should have better say it is isotope. More careful student may notice it's carbon 14. The normal carbon is carbon 12. That consists of 6 protons and 6 neutrons. So this carbon 14 are isotopes of the normal carbon nuclei. Okay, it consists of 6 protons and 8 neutrons, 2 more. Okay, and so therefore, if you got 2 more neutrons in your nucleus, then it becomes more stable. It becomes more unstable. So usually we identify isotope with instability. Okay, yeah. So this is isotope carbon. In the last hour, we talked a lot about the damaging radioactive decay. But sometimes the decay are not that damaging. For example, this one, the electron it emits is not that damaging because the energy is very, very small. But it's useful. This process is used for carbon dating. 碳纪年, remember? Okay, because in nature, there is a certain proportion of the isotope carbon among all the normal carbon. Okay, and this process will occur very, very slowly, as I will describe very soon. It occurs very, very slowly. So the amount of the isotope carbon in your body, or a tissue, or a material, actually will determine the age of this body or this. So for the historic study of artifacts, the carbon dating is actually very, very important. Okay, it's not damaging at all. This is radioactive decay. Let me tell you. And so isotope for carbon decay, as I say, it got 2 more neutron than the normal carbon, so it's very, very unstable. It prefers to transform one of the neutron into a proton. If one of the neutron transform into a proton, then it becomes a normal nitrogen. Normal nitrogen consists of 7 neutrons and 7 protons. Okay, so it's much, much more stable than this one. So that's why this decay will occur at all, because it seeks to go from a very, very unstable nucleus into a very, very stable nucleus by transforming one of the identity of the nuclei inside it. Okay, nucleon inside it. Okay. Now we can start to enough for the qualitative for the quality of this decay. Then we can go ahead to do some quantitative calculation. The experiment is very, very simple. We just collect a large box of carbon isotope nuclei, and then observe how many of them will stay every unit time, every second, for example. Okay, and we now, yep.
You can go back to the graph. To the graph.
Yep.
Right. My understanding of it, right, of the decay equation is that you start with a quantity and then over a period of time it decreases, right?
Right.
Does this decrease or decay ever get to the point of 0?
No.
Why is that?
After we solve the equation, you will see. Okay. It never reached 0, but it could decay to a very, very small number. It's called exponential decrease. I'll get back to that. So our experiment, a huge box of carbon isotope nuclei. And we now know that from calculation, some calculation, and also some fundamental physics, we are not able to predict whether this single nucleus will decay or not in the next second. It's impossible. Okay, some of them will decay, some of them will not, even though the nucleus are identical, as I told you. Even though the nuclei are identical, 一模一样的碳原子核，它就是有些时候会衰变，有些时候不会衰变。You have no way to tell. You have no way to. Unlike cabbage, you can say, well, this will grow, this will not, because you have some knowledge about the environment or initial condition. But here, no. Even though the initial condition is the same, even though the process is the same, you just cannot tell whether it will decay or not. But very, very strangely, modern physics can predict how the probability this will occur in the next second. 这件事非常非常重要，让我用中文再讲一次。现代物理呢，可以预测，我们没有办法预测这颗单独的这个碳的原子核会衰变或不会，但是我们竟然可以预测，它过了1秒钟之后，有一定的 probability gamma will decay。那 if gamma probability will decay, that means 1 minus gamma 的 probability 就 will not decay, will stay as the isotope carbon. But there is a probability of gamma, it will become into a nitrogen. So you can observe the number of carbon nuclei in your box to determine this gamma. That's the key of our calculation. Okay, any question? This is the starting point of our whole calculation. If there is any question, you better ask now. So the original nucleus will disappear with the probability of gamma per second. That means the original nucleus will stay with the probability of 1 minus gamma. Okay, so even though you do not know whether a single nucleus will decay or not, but if you have a huge box of the nuclei, then you can predict the number of decays that will happen in the next second. Remember, what's probability? Probability means that you perform the experiment several times, then you can predict the outcome. But if you only perform the experiment once, you can only say with certain probability you will do that, with certain probability you will do that, you will not, etc. But if you perform the experiment several times and collect all the data and do the statistics, you can predict. 几率就是这样嘛，单一次的掷骰子，你不知道结果是什么，但你掷了1800万次，你就知道了。你的1800万次的骰子里面，会跟不会的比例，刚好就是你的几率的比嘛，对不对？不是这样吗 ？Probability idea 是这样啊。So tell me, you can from the data you have here, you can easily predict in the first second, because the probability to decay is gamma, then it is easy to understand that in the next second, gamma n is the number this decay will occur. Is that okay to you? N is the number of the nucleus. It changes with time. So this n is a function of time. So this is our target. This is our target. We want to solve n. Okay. And so n is the number of the nuclei. If the probability is gamma, then in the next second, gamma times n is the number this decay will occur. If gamma n is the number of the decay to occur, every time a decay occurs, n decreases by 1. N decreases by 1. Okay, so that means dn dt is equal to minus gamma n. Friends, so decay equation. The reason is pretty simple. Okay, per second, dt means per second. Per second, the change of the number is actually proportional to the probability times the number at that time. So that's why the n dt, the first derivative of the number, is proportional to the number itself. Put in another way, the more nucleus you have, then the more decay will happen, and therefore the change of number will be more. at end of the process, if you have only two particles, nucleus remaining, and then the number of decay to happen will be very, very small because I got only two to do the decay. Okay. But in the beginning, when I have a lot of particles, a lot of nuclei, then I have a lot of chance for this decay to happen. So the NDT will be very, very large at the beginning, very, very small at the end. And put it mathematically, they are proportional to each other. Decay equation. Okay. This is actually the same kind of reasoning if the number is reversed. It means when we are talking about number increasing. The typical example is germ growth. Germ, COVID. COVID growth is COVID, COVID virus. Okay. When a germ or COVID or microscopic object, when they grow, actually the growth, it is also, they satisfy also almost the same mathematical relation, because the number for every virus, the chance for it to grow is identical, just like the probability for nucleus to decay are the same. It's the same thing. So for the virus, it is now the probability for it to disintegrate, split into two units. The increase in the total number of virus, the probability is the same. Okay, so therefore now the NDT is positive gamma n. Okay, instead of minus gamma n. But everything else is the same. All the reasoning is the same. So the same kind of reasoning, the same kind of equation with a different sign actually also apply to the growth of the germ or microscopic objects. Okay. Is that okay? So that's why this decay equation, and then this equation is the same equation we have in the Vx, the horizontal. Remember, again, we are talking about what we want to solve. Is the decay equation, is the horizontal velocity, and they are the same equation. Although it is much harder to argue why the rate of change dv dt is proportional to itself. So that's why you need to write down the whole equation of motion to arrive at this conclusion. But for the decay equation of radioactive nucleus, it's much easier to argue. But anyway, easy or not, the two equations are identical. Okay, now, finally, let's solve it. In my solution, I usually have 3 steps. The first step, or I should say approaches. The first approach, I call it method 0. Method 0 means, well, it's not rigorous at all. It's not mathematical at all. It's more intuitive. It's by guessing. 直觉. Okay. So I'll do the method 0 several times because it's intuitive. And then I will go to method 1 and method 2. Method 1 and method 2 are more mathematical and systematic. Okay. As Feynman say, if you could not solve a problem in 3 different ways, you don't understand how to solve it. Feynman 说过，如果你一个问题不会用3种方法解的话，你并不会解。Okay, so in our class, every problem we probably do it 3 times. Okay, no. I'll do it 3 times in the transparency. Probably will present it 1 or twice in the lecture. Okay, method 0. Method 0 is intuitive. Not rigorous at all, so don't argue with me. It's intuition. Look at this equation. dn dt equal to minus gamma n. So read it with your mind. Simple. You only say, as I say several times, the first derivative of the function nt is proportional to itself. So if you want to solve it, find a function that behaves like that. First, you know polynomial couldn't be. 多项式不会是解， Because you know that every polynomial, when you take derivative, it decreases the number. Forgot how to do it in English. When it's n, doing first derivative, it becomes n minus 1. And take the derivative again, it becomes n minus 2. In Chinese, it's called 幂次会越来越低. Sorry, I forgot how to do it in English. So n becomes n minus 1, and take a derivative becomes n minus 2. So there's no way a polynomial could be proportional. The derivative of polynomial could be proportional to itself, right? 多项式的微分不会跟自己成正比 ，no hope. So forget about polynomial. How about sine function? Triangular function. And we know that there's some hope, but still not true, because the derivative of sine is cosine. Although if you take the derivative again, it comes back to sine, but if only have one chance of derivative, then sine will change into cosine. Cosine is of course not proportional to sine, right? Okay, so again, it does not fit. However, after your calculus class, you know that there is a function directly will fit the behavior you need. Exponential function. 应该教到了嘛，对不对？好 ，exponential usually this e is the 1 point 哒哒哒哒哒，哎，不是2点哒哒哒哒哒那个 natural number. Okay, so the derivative of a exponential function usually we say it by e to the x power. Then e to the x power when you take derivative is derivative equal to itself. Okay, so that's the thing that we want. This derivative of exponential function is proportional to, it's equal. Here it's equal to itself, not just proportional. It is equal to itself. Actually, this is a defining property or defining characteristic of an exponential function. Some of the mathematical textbook will use this as a definition of an exponential function, the name, and proceed to derive it that this kind of function look like this. Okay, so some mathematical physics will do it backwards, okay, for the rigors and for the beauty. But for us, exponential x is the derivative, taking derivative is equal to itself. I assume there's no problem here. And if exponential function derivative is itself, then the exponential function with the constant, for example, e to the bx, when you take the derivative, by chain rule, must equal to b times e to the bx. Any question about this? Chain rule. Okay, so exponential bx, taking the derivative is equal to be bx. Just what we need. Okay, so that's why we call method 0. There's no argument here, it's just by intuition I know it is there. Okay, so that's why I call it method 0. That just means I need to take a call from my daughter. 我要接一个电话，稍微等我一下。You can. That's just one or 2 minutes, okay? Hey, hello. Hey, I'm in class. I'm a prep. It's a. 好，那你晚一点点，没有事的话就晚一点打给我啊。You okay? Okay. Call me later. Okay, bye bye. Sorry. Where am I? So if you compare the two equations, this one and this one, you immediately see that how we can solve the equation. You just take the constant b as minus gamma. Then got a solution. Simple. So you see that mathematics is simple. So you pick b as minus gamma, you get a solution. Exponential minus gamma t. You can check for yourself. You plug this solution into the equation, it's solved. But unfortunately, this is not the only solution we will get by guessing. You can guess again. Why could we not multiply the equation, the exponential function, by a constant? We call it c here. Remember, when I multiply the exponential function by a constant c, it actually satisfies the same equation. Just look at this derivation. If we plug in c instead of c exponential minus gamma t, instead of exponential minus gamma t, the additional thing you multiply here does not take any derivative because it's a constant. So immediately fly away from the derivation. Okay, so it goes to the front, and then you get the exponential minus gamma t over dt. And exponential gamma minus gamma t over dt is just equal to minus gamma exponential minus gamma t. Obviously, right? So this c does not take any derivative. And then this c go back to, after this step, would go back to the exponential function and becomes n. And therefore, the starting point of this equation, dn dt, is equal to minus gamma n. It's just the equation we want to solve, isn't it? So that means multiplying by the solution we intuitively found by a constant c does not change the fact it's still a function solution. So that's trouble. This solution is the trouble because in this solution, we not only have one solution because we have no idea what c is, isn't it? 这个 c is unspecified. Usually call it unspecified function, constant. That means you can put in any constant and you still get a solution. So we not only get one solution, we get an infinite number of solutions. That's what you will always, almost always encounter when you solve differential equation. It's very, very different from algebraic equation. 在代数方程式里头 ，usually 你不会有没有解出来的东西。1加 x 等于2 ，x equal to 1. What else? Right? X equal to 1 is the single solution you will get. However, when you solve a differential equation like here, actually, I got tons of solutions that can satisfy the differential equation. You will encounter this kind of difficulty every time you solve differential equation. So that's the first lesson 101 of ODE. Okay, so infinite number of solutions is natural in difficulty you will encounter here. In this manifestation, it is a constant c, which is unspecified. Again, when I say unspecified means you can put in 1, you can put in 2, you can put in 2.55. Whatever number you put in, you still got a solution. Okay, our infinite number of solution is a common feature. It's a common feature. Okay, so, but those students may have solution for this. We haven't put in the initial condition yet, right? So, to determine the number of the nucleus, don't you need to tell me how many nucleus we start with? Of course, it's physics. It's obvious. We need to tell you N0. N0 is the number of nuclei at the beginning of the time of t equal to 0. We call it N0. If you did not tell me how many eggs are in the box, how could I tell you how many eggs are there in 10 minutes, right? Okay, you need to tell me the starting point. It's obvious. It's obvious, okay, from the physical point of view, okay? Therefore, this kind of thing is called initial condition. Remember this term, 起始条件, okay? You need to tell me the initial condition, then I can give you an answer. Okay, it's obvious mathematically. N equal to c exponential minus gamma t. Then you can plug in t equal to 0, and you immediately see that c is just n1, or in reverse, n1 is equal to c. Oh, c is fixed by the initial condition. That's the official name of this game. The c, the unspecified constant, is fixed by the initial condition. Without its initial condition, the first order differential equation has infinite number of solutions, but if you put in the appropriate initial condition, the ODE has just one solution. That's the one. And I guarantee there is one. Mathematician will guarantee there's just one, not two, not three, just one. If we put in appropriate condition and the solution that could satisfy initial condition and the equation of motion has only one. It is actually very obvious geometrically. Geometrically. Here on the first diagram, I write all the solutions, the graph. Let me put this. This x is the function of n. Maybe I should change this to n next time. And this is time. So the solution exponential minus gamma t is this. Because c is unspecified, so we got infinite number of lines of solutions. Okay? But if you, so infinite number of solutions. But if I fix the initial condition, that is, I tell you that the initial at t equal to 0, the function has to be here instead of here, instead of here, instead of here. Then there's only one line that will pass, isn't it? Only one. Couldn't be two, couldn't be three. And it has to be one. Ladies and gentlemen, so among infinite number of exponential lines that satisfy the equation, only one will pass through the initial condition. This kind of result apply to almost all the differential equation. Next week, we are going to go, maybe next week at the end, we will start to talk about the ODE of second order. When there is a second order derivative, the initial condition will consist of the initial condition and the initial speed velocity. We need two initial conditions. But here, because our derivative is only first order, therefore we only need one initial condition. Okay, one initial condition is enough for this. Okay, and as I say, it's normal for the equation to have infinite number of solutions. Here I write down the free-falling objects, their equation of motion. It's so simple. You can see that at the end of the day, I also have unspecified constants. If you follow the argument, okay, we don't have much time for this, and it's so simple. But if you have time at home, you can follow this derivation and see that the equation of motion for free-falling objects. Also, when you solve the equation, you also have a unspecified constant in it. That means the equation does not have just one solution, but infinite numbers of it. However, just the same as what I have told you here, if you put in the initial condition here for free-falling objects, you need to tell me the initial position, you need to tell me the initial velocity, and then the two conditions will determine C1 and C2. The unspecified constants are specified as V0 and Y0. Therefore, there is only one solution, and this is your destiny. Remember, equation of motion is to determine your destiny, your future path, and that is it. No argument, no ambiguity, 没有任何的不确定性. That's the key of classical physics. No uncertainty. As long as you have the equation of motion, as long as you have the initial condition, your whole future, how this particle will move, how this particle will move, are already determined like a machine. So that's why it's called mechanics. 所以力学原来应该是机械学啦，因为你看嘛，所有东西都决定了。你告诉我的 equation of motion， 你告诉我的你的 initial condition， 你未来的命运都全部决定了，像一台机器一样。所以力学其实是机械学，其实机械学 mechanics， mechanics means machine. The world is like a machine, and key to the whole argument is that for ordinary algebraic equation, there is no ambiguity. I call it no wiggle room. 你没有什么好啰嗦的，没有 ambiguity. 2x plus 1 equal to 2. X can only be 1/2. What else? But in equation of motion, for differential equation, it has to So no wiggle room is just like a very small Ferrari roadster. However, in equation of motion, you at least need a SUV because you need to adjust the initial condition, right? So when you solve this kind of equation, it needs the freedom because you need to put in the initial condition. Okay. Only after you put in the initial condition, then the solution becomes just one. Okay. Okay, so any question? This is very, very key, simple, but very, very key aspects of equation of motion solving. I hope you can understand. You'll come back again and again in the next couple of weeks. Okay. 不难，对不对？好 ，Yeah, just remember it. Now, let me show you some of the property of this exponential function, n0 times e to the minus gamma t. Because it happens so often in the physics world, so some of the simple property will feature very, very often in your learning. For example, this kind of function we usually call it exponentially decreasing function of time. Exponentially decreasing time because it's exponential function, of course. This kind of function has one most important property. That is, for the key feature is that it takes the same time to decrease by half. This is half, sorry. So for the number to becomes 1/2, you record the time, and then for this number to decrease again 1/2, the time is the same. It's not difficult to derive because if you make a ratio between nt2 over nt1, that is the ratio of the number between two different times, and you plug in the solution, you get exponential minus gamma t2, exponential minus gamma t1. C and C cancel out, and then it is easy to argue. This is equal to exponential minus gamma t2 of minus t1. That means if the ratio between this and this is 1/2, that means gamma t2 t1 is a constant. This constant is usually given a name called 半衰期, half time. Yeah, in English, half time. Okay. Sometimes the notation is t1/2. That is the time for the number to decrease by half. So for the number to decrease by half, t2 minus t1 had to be equal to gamma, 1 over gamma times log 2. This is a constant, this is a constant, so this is a constant. So the time difference are the same. The same half time will determine the time for the number to decrease by half. That's very strange. Usually, it is the number that is decreasing is the same. No. It's a ratio that decreases per unit time. Okay. This is a key feature of exponential decreasing function. And so this half time, t1/2, which is proportional, more or less proportional to 1 over gamma, the inverse power of the gamma we have here, the probability we have here, actually determines how fast a radioactive nucleus will stay in nature. For example, this is carbon, half time of carbon-14 isotope is about 5,700 years. So it's quite a long time. That's why I told you that we can use the isotope 14 carbon to determine the history, the age of artifacts or a body we discover in architecture site. Because it takes about 10,000 years for the carbon-14 to decrease by half. And this is not the most notorious case. For example, the really damaging nucleus, iodine 129. I hope I pronounce it right. Iodine, I think. Iodine, yeah. Iodine 129, the half-time is 1.6 million years. 1.6 million. No, sorry, 16 million years. 16 million years. So it's quite a long time. That's again why the nuclear power plant could be quite dangerous if the nuclear active material leak outside their oven. Because one of the product is this. And it takes 16 million years to decay. We stay there forever in our lifetime, okay? And iodine is something that our human body will absorb because of our 甲状腺. We will absorb the iodine very easily. So that's why usually when we prepare people from a nuclear disaster, we usually give them yen, the salt with real iodine, not the 129 isotope. Okay, so that if you take enough salt with normal iodine, maybe when some of the leak radioactive iodine reach your body will reject it. That's a typical way for us to prevent damage into our body from the nuclear disaster. Okay, that's the stuff. So in the process of 16 million years, the radioactive is always there. Yeah.
我想问那个前一页的 PowerPoint
对。
那个平均寿命数量变成1/1，指的是什么意思？
哦，我很快的收过去，就是它跟这个其实是非常的类似。He's asking what is this average life? This is half life. This is average life. Okay, so basically they are almost identical to each other. 1/gamma, 1/gamma, but there is a log 2. They are not identical, but the purpose, the property are more or less the same because they are all 1/gamma. Then why I say it's the average age, because when the time past gamma, we usually put this gamma into inverse as T/tau. Then that means when this T equal to 1 tau, then the N will decrease by 1/e. Because you put in tau here, then this will become e to the -1. Again, if T is equal to tau, that means after 1 tau time, the number will become e-1. 就是你过了一个 tau 时间了以后，那么你的比例就会变成是1的负1次方。那1的负1次方，1是2点多嘛，对不对？所以呢，大概就是2点多分之一这样子。这就 usually we call it the average life to estimate how long this nucleus will stay. But even easier to use is half-life. It's easier to describe. Okay, half-life is that when the number decreased by
它跟半衰期，其实它就是半衰期。
半衰期是变成一半，1/2，对不起。From here to here, it decreased by 1/2. But if it decreased by 1/e, 1e is almost 2.7，对不对？那所以2.7应该就比2要来的小嘛。对不起，来小在这里 ，right？ 好，所以呢，从这里到这里这段时间就叫做 half time. But they are intrinsically almost identical. You only need to multiply by log 2. Then when to use it? When you want to know how long it takes for this guy to decrease by 1/2.7, then it is half-life. But it's always easier to use half-life because 1/2 is much easier. Okay, so if you ask how much time it takes for this number to decrease by half, and that's half-life. Easier easier especially for technical guys. 半衰期. Okay, so that's why we always quote half-life when we talk about radioactivity. Okay, then so I have some data about you know that maybe as this. I actually got some description about the Fukushima, I think. Fukushima nuclear disaster in Japan. Okay, they store all the radioactive water, wastewater, when they cool down the nuclear power plants into this tank. 一个一个的 tank 都是里面都是水。Not just water. If it's water, then just give it out to the ocean. But it's not, because inside this water, some of the hydrogen is not hydrogen. It's isotope hydrogen called tritium. Hydrogen has the nucleus of hydrogen. It consists of only one proton, but this isotope consists of one proton plus two neutrons. Isotope means the property, the chemical property of isotope are the same as the original element. 所以氢的同位素就跟氢本身化学性质完全一样。But it's radioactive because it's got two more neutrons. They don't like it, so they want to disintegrate, as I told you. So usually it will undergo a beta decay, so that one of the I think it's beta. Oh yeah, it's a beta decay. So one of the neutron will become proton. So isotope will become helium, because the nucleus will then, after the beta decay, will have two protons. Nucleus with two protons is helium. So this is something called tritium, or the isotope hydrogen nucleus will decay into a helium nucleus. Okay, so actually the Japanese have done a lot of job to filter out all the radioactive damaging material. 它把它过滤掉了哦。So the only thing they cannot filter out is water, or water with tritium. 因为它 the physical the property of tritium water is totally the same as ordinary water. There is no way to differentiate them with each other. Okay, therefore they cannot filter out these radioactive water. If I can call it radioactive water. So they store it and store it. It takes a long time and it keeps accumulating. So I think it's next year they start to release it into the ocean. So you may ask, how damaging is it? How damaging is it? It's not that damaging. I think I have data here. For example, the half-life. So half-life of this tritium nucleus is 12 years. 12 years. So that means all these nuclear wastewater, after it was released into the ocean, after 12 years, half of them will disappear. Not disappear into helium nucleus. So 12 years is not that long. So if you wait long enough, then those water released into the ocean will no longer be there. Or I should say, not radioactive at all. However, you may ask another question, how damaging is it? Fortunately, it's not very damaging. I told you it's a beta decay. But this beta decay, the electron fly away with very, very small energy. Very small energy. It could easily be absorbed by our body. By skin. It never penetrate. Because the energy is not large enough for tritium decay. Okay, how about tritium decay? Okay, so more or less, this process is safe. More or less, it's safe. But I mean, this not just but the world is very complicated. The problem is the reputational damage to the fishermen is huge. Because everybody thinks maybe some of the fish from Japan will have some problem. Well, it's not. But the reputational damage probably will take years for people to absorb the fact this is not damaging at all. Anyway, so now we have solved the decay equation. Now we can put the solution back to the question we raised in the first place. That is the velocity, sorry, the horizontal velocity, Vx. Now, do I need to solve the problem again? No, of course not, because the solution is totally identical. That's the key. After I solve it once, I don't need to solve it the second time. Vx, I immediately know the solution is c, a constant, times exponential, the minus k over m times t. Maybe I should give you the transparent. The comparison between the two equations again. Where is it? He's so early. Sorry, yeah. So this is here. So this is the decay equation, and this is the equation for horizontal velocity Vx. So k over m corresponds to gamma here. Therefore, if our solution for the decay equation is exponential minus gamma, the solution for the Vx will be easy to write down here. Exponential minus k over m times t. Exponential decay. Okay, and again, I need an initial condition. Here, the initial condition is the initial velocity. Okay, Vx0. That's the velocity at t equal to 0. And you could easily see that it is equal to c. This c designates the original velocity. Therefore, with the initial velocity given, then I can write down the direction. I can write down the velocity, the solution, right away. Vx equal to Vx0 exponential minus k over m times t. And all the discussion can be applied here. Decrease by half, and half times the same, blah, 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 blah. I don't need to told you it for second time. That's the beauty of mathematics. Let me show you one more thing. This exponential decreasing function is the inverse of the exponential increasing function. Okay, here it's decreasing, but if you take out the negative sign, you got the exponential increasing function, exponential x. Okay, exponential x could be expanded in terms of an infinite series. I think it's a standard topic in calculus. But if you haven't learned it yet, you just take a look at the result. And sooner or later, your calculus teacher will teach you why it is so. But the result is simple. Exponential x could be expanded as e1 plus x times plus x squared over 2 factorial . It's an infinite series. You cannot cut it anywhere. But if x is not very large, then it will become less and less important. But if x is large, then you have to take into account everything. Okay. The point is, if this exponential function can be expanded in this way, I can argue that exponential decreasing function decrease faster than any polynomial inverse. In Chinese, 指数递减比所有的递减要更快。要记得这件事情啊，指数递减比所有的递减要更快。x 平方也是递减啊，x 三次方也是递减啊。但是 let me show you, exponential minus x decrease faster than any power of x. The argument is very simple. I just take exponential minus x over x to the minus n, and ask what it approach when x equal to infinity. Okay, 当 x 呢越来越大的时候 what this will approach? The solution is simple with this infinite series, right? Because exponential, I should do this first. Oh, it's here. Exponential x. No. So I do it here. So exponential minus x, x to the minus x minus n. I take the ratio of them and see how they approach, to see how they approach 0 faster. Then exponential minus x could be written to is equal to the inverse exponential x. X the minus n power is equal to the inverse of x to the n. But remember, exponential x consists of infinite series of polynomial. Okay, so sooner or later, when x becomes larger and larger and larger and larger and larger, we always has a term that the power will be larger than n in your question. Okay, 我永远一定会有一个项，它的这个东西呢比 n 要来得大。So when x approaches infinite, this thing always approach 0. So if this approaches, so that means e to the minus x decrease much faster than x to the n. Okay. On the other hand, if we talk about exponential increasing, for example, if we can take exponential x over x to the n, then when x goes to infinite, it will approach infinite. Okay, so in common language, exponential increasing function increase faster than any polynomial. It's a very, very important property. So the speed the germs will propagate actually is an exponentially increasing function. Another example is financially, that's a couple of days ago when Chia-Hung announced in his press conference, NVIDIA's the revenue increased very, very fast. How fast? How to describe a really, really, really fast increase? He said, computing demand is growing exponentially. Remember this word. When people say it grows exponentially, that means it is an exponentially increasing function. It goes faster than anything else. It is called exponential growing. OK， 好，指数增加。OK， 好，所以当你讲指数增加的时候，就讲你比什么增加都还要更快的一个增加。好 ，we call it growing exponentially. 好 ，growing exponentially. OK， any question? Do you want a break about 5 minutes so that I can just talk about 再讲15分钟 I'll talk about another 15 minutes， 好不好 ？OK， 好，我们休息5分钟，好，然后我再讲大概15到20分钟就可以了，好。 啊，是，串一个，差不多 filter 掉，对，但是，那可惜了，因为这个不是什么，就是太专门的科学啊，就很简单的科学。对科学家来讲，我们对这些当然是上面还有测，所以呢，他说 filter out， 就是 filter out， 一测就知道了，大家都 argue。那测不出来，清不掉的，就是滤不掉，就是因为它的那个穿实在太严实在。你说其他有没有滤掉？其他有放在比较高的，像那个就很严重，那个0.12就非常。那就很容易就测得到啊，因为就拿其实我办公室就有一个啊，因为我楼下是那个放射系实验室，他们有一个，他们这是纪年啊，那个没有放射性，但是不好意思。就给楼上的一个盖革技术，盖革技术就有一个东西在那里，只要有这个贝塔射线打过来，咚就有神奇的技术。这已经是100年的理科学了。所以如果说你有任何的其他放射性的东西，他会知道，那就把它低调就好了。啊，所以当然啦，老实讲，你讲的没错。We need to monitor， 就是 internationally need to be monitor。日本好像做的还 OK 啦，它不是太那当然even more transparency。那这种就是要大家相信彼此，就像你会这样的问题，对啊，那相不相信？那很简单啊，你就叫美国的科学家来，叫美国，那大陆不爽，那大陆来。那这个都有，还科学有 good thing is that there is an international standard， 所以你要问什么问题，没有写报告的时候，对，我觉得这做日本做的 more or less OK 了，所以你看过了这么多年，你看当初Chia-Hung大叫，不是当初讲，当初大家会抗议，为什么也是合理的，想大家讲啊。他那个过了已经1年多了，他要生气的时候爆炒，那中国要是真的发现，很简单嘛，你中国只要他来上去，到一个更高的标准，对科学你可以默认，啊，所以这一部分的问题就是这一部分的科学已经是很奇妙了，做到非常好，就不跟我们一般在社会上的感觉。不太一样，社会上会觉得说你知道，但是科学家会觉得是可以，因为这我完全都知道。你的问题是1600年、万年，当然就不知道该怎么，就是那个1600万年的半衰期，那你还真不知道怎么对付，你不知道怎么对付，但是它的科学已经非常清楚。就是说，我们对它还是非常了解，所以科学家比较伤心的是，大家不要一直说不知道，因为我们都知道。当然要怎么解决是很多的问题，比如 ionic 完全你它不烧北，比如光就来个原子，虽然只好 filter out 有啊，它里面对着一大堆点1、2千，那 filter out 他们怎么处理，那我还是不知道。但如果就实验本身，那些他可能就要自己那他还真不晓得，对，所以我们应该科学有讲一下。Okay, final 15 minutes, 2 more transparency, and we are done today. Okay, so the final 2 transparency are actually very abstract and very simple and very useful. Okay, this method is called separable function. I call it, and this is my method 1. Remember method 0, method 1. Method 0 is intuitive. Okay. A lot of you may object now. You are guessing. 对，用猜的。As solving differential equation takes a lot of guessing. You will see very soon. When we reach the second order differential equation, guessing. And all the lecture in the last few hours, guessing. We guess the function is like this, and do this and do that, and tell you the result. You may cry for systematic and more abstract way to do ODE solving. Now, let me show you. There's a simple, if the equation is simple enough, yeah, actually there's a method, a systematic method to solve the problem systematically, mathematically, abstractly, generally. This is called separable function. Let me use the dn dt decay equation as our first example. And the next transparency, I'll show you the general derivation, and we are done. Okay, so this method again, separable equation. Okay, method 1. Actually, it's very simple. dn dt equal to minus gamma n. Now, instead of just look at it and guessing what the solution is, I can manipulate it in another way. I can pull the n on the right-hand side. We can pull the n on the right-hand side. I'll translate into English later. I will pull this n on the right-hand side to the left-hand side. And then, if I have done this equation on the left-hand side is a function only of n. There's no t. On the right-hand side, there's t and no n. That's why it's called separable function. The function and the variable can be separated, keeping one on the one side and the other on the other side. That's the point. Okay. And there is some physical interpretation or mathematical interpretation of this. This equation, when written in this way, relates a very, very small change of number with a very, very small change of time. This equation is to describe this thing. Okay, the ratio between dn and dt is described by this equation. But mathematically, when you have done this, I can take integration of both sides. It's as simple as that. This is probably one of the most common differential equation solving technique you will encounter in your college life. Okay, so concentrate the function and the variable on both sides, and then integrate. Take integration. Okay, because the n is concentrated on left-hand side. When you do integration, you are doing the integration over n instead of t. So it's calculable. The point is, it is calculable. On the right-hand side, there is no n number function, but only t. So when you do an integration, you're integrating over dt. Again, it's calculable. So both sides are calculable, and you are done. Right? It's simple as that. So I can finish in 5 minutes. Okay, so the left-hand side, 1 over n, integrate over dn, everybody can tell you is a log n. On the right-hand side, dt integration is just t. Almost done. But remember, when you take integration, I can always add a constant number to it, because this is the equation. When you do, and integration is the inverse of differentiation. So actually, for this, when you take the differentiation, this becomes this becomes this, and c prime only disappear, because the derivative of a constant is equal to 0. So you can always, remember this, you can always add a constant, and this solution always corresponds to this solution. Is that acceptable? 你永远要记得，当你做积分的时候，你永远可以再加上一个常数。Okay, oh, don't miss this c prime. Okay, then log n equal to minus gamma t plus c prime. Then you take an exponential function on the both sides. The left-hand side will give you n. The right-hand side will give you exponential, the minus gamma t times exponential c prime. Let's call it c. Okay, the same solution. So this is not guessing. This is calculating. If this fits your flavor, then that's called separable function. 所以之前我们用猜的，这个就是一个系统性的一个做法来解 decay equation。再一次，我 separate the function and the variable on both sides of the equation, and then I can take integration and equate them. That's it. Okay. And now you see why putting a C prime is very important. Remember, without this C prime, there is no C. If there is no C, then you cannot put in initial condition. As simple as that. So again, when you take integration, remember you can always add a constant without changing your result. Okay, so because again, C is a unspecified number, we arrive at infinite number of solution. However, with appropriate initial condition, there's only one solution, which is n0 exponential minus gamma t, just like what we have already got. Systematic way. So this is very inspirational. This is very inspirational. We can generalize it to a lot of equation of motion, differential equation of motion, if your function is separable. So method 1, the extension of method 1, we are going to apply it to a general differential equation. Remember here now, because I'm changing my face to a mathematician, so the equation becomes dy dx instead of dn dt. Remember, when I change my face from physics to mathematician, for general discussion, I'll revert to y as a function of x. So as I say, the most general, the simplest equation of motion, differential equation of motion is dy dx equal to a certain function of y and x. Let's say y fyx is separable. By separable, I mean it can be separated into a function of x over a function of y. Okay, this is special case. 这是特殊的一个情况。I'm going to show you if this is 对于像这样子的 equation, for this kind of equation, the separable equation, we call it the separable equation, and the same method could be applied here. 刚刚讲的那个方法就可以用在这一类的问题上面。那刚刚的这个问题 dn dt is equal to minus gamma n, of course it's separable because on the right hand side there is no t. So there is no q, there is no px when you apply this formalism to the decay equation. Think about it. Okay, so the statement is simple. Let's start to study this kind of separable equation. Separable equation f could be separated into a function of x and a function of q. Okay, and it's easy. The principle is to concentrate all the y function to the left-hand side, all the x variable to the right-hand side. So because it's separable, so that's achievable. So I multiply this qy, move the qy to the left-hand side, move this dx to the right-hand side. We arrive at a qy dy equal to minus px dx. This is identical to what I did in the decay equation. Okay, and then it's easy to see that the left-hand side consists of only y, the right-hand side consists of only x, and we can take derivative integration of both. Remember to get a c, to put in the c, and then you got the solution. Okay, done. That's a so-called separable equation. The separable equation. It's just as easy as that. Of course, you need to give me q, you give me p, then I can do the calculation. I think I have one example. Yeah, this is one example. I think it's useful, right? So let me give you one example so that you can understand this general idea. Okay, this example is dy dx minus px, a function, not a constant, it's a function of x variable times y equal to 0. Very abstract, but it's useful later, next week. This is example 1, dy dx minus px y equal to 0. First step, I will just pull this thing to the right-hand side. So dy dx equal to px, y. And then concentrate all the y to the left-hand side, so it's y 1 over y dy. Concentrate all the x to the right-hand side, so it'll be px dx. And then I take an integration. I skip several steps, but I think it's not that difficult to trace. Okay, let's concentrate all the y to the left-hand side, concentrate all the x to the right-hand side, and then when they are equal to each other, I can take integration, and they're still equal. They are still equal. Okay. Therefore, 1 over y, the integration with respect to y, equal to log y. And px depends on what px is. Okay, it's given by the question, so I keep it in the original form, px integration. But remember to plus a c prime, and that's the solution of y. Okay, so y is equal to a constant times exponential p integration. That's the solution. Very simple as that. This formalism will be used for next week when we start to solve the vertical velocity equation of motion. Okay, take a look and think about it. I'll probably give out an exercise this week. There will be one exercise this week. Okay, 那个教的时间就是2个礼拜以后。The method we'll be using is this kind of separable. Separable. Let me announce something. First of all, our midterm exam is still about a month away. However, I can tell you that I will allow for you to take in a piece of paper with formulas. 你可以自己写一张有计算有公式的啦，我意思是 ，OK？ Because you know we have so many formulas, okay, accumulating over the course of the semester, okay? So if I want you to remember everything, it becomes very difficult, and it's not useful because you have ChatGPT. You can also always ask GPT to give you the equation, right? So for our exam, you are allowed to take one piece of paper. Do not take the iPad or other 3C because you can ask ChatGPT to solve the problem for you. No, but you can take in a piece of paper, written paper with formulas of your choice. 你自己选，你要写什么公式，你随便你 ，OK？ 好，就是一张纸。2张可以吗？不行啊，3张是A4 size paper with formulas on it. Okay, fine. Yeah, but that's back and front. Okay.
正反两面都可以。
Yeah, good. Back and front, yes. Okay. Usually only allow front, but okay. Back and front. 最好不要，一般计算机比较好。We don't need that much calculation, and because a lot of calculator nowadays almost like a computer, you can do anything about it.
最好不要所以可以。
No, I only allow ordinary calculator. 一般的计算机。有没有什么问题 about this rule 有什么关系？
一般计算机
工程计算机可以。
不行啦，
就
不行，因为工程计算机里面可以算很多东西啊。我们的计算其实 no. For our class, we don't need very advanced calculation.
可是需要微分跟积分。
So that's why I don't allow, because I wanted to do you by your hand. Hey, come on, you physics department students, you cannot rely on calculator for the rest of your life, right? No. Do calculus yourself.
工具就要用。
Yeah. 好 Let's settle that. One piece of paper. No. 我们的积分不会太难啦。Our calculus is not that difficult. Okay. Or I will be in the class, so you can always ask how to do the derivative. I'll give you some hint. You still need to do it yourself by hand. You are physics department student. Come on, give me a break. 不会啊，不会很难。By the way, 我的那个 homework， 等一下可能要下午或者晚上才会出来。My homework, the problem is almost identical to the problem this year. Okay, so you can see how difficult it is. The level of difficulty. 从我的那个习题里面就会看得出来。
好像有。
你说考试的习题才会就是后问。
对，所以你们的习题就是我去年的题目啦，对不对？
可以吗？
啊，
就是可以找得到考古题。
我的习题就是考古题啊。
不是啊，这上面也有。
Yeah, I'll give you that. I'll give you that. I'll give you the this year's problem, but it is in Chinese. It's in English. Yeah, it's in English. It's okay. Yeah.
在你的网站上对。
到时候，现在还没有。It's still months away. I tell you this in advance, so that you don't need to remember all this formula. 你不要去记这些公式啊，太多了啊，人生记不了那么多事情啊。Okay, I tell you this in advance of the exam, so that you don't need to remember all these formulas, but to grasp the method and the spirit of solving this equation. Okay, that's the key. I told you this first. At this moment. Okay, any other question?
Do we have to derive those formulas in the exam? Do we have to?
No, usually don't. You just use it. So that's why I told you that you can bring a piece of paper. For example, if you write this down, you don't need to derive it in exam. You just say, oh, my paper told me. Just joking, but that's the point. You don't need to prove it from the first. Wait, this is not. It's an exam. It's not a proving demonstration, right? So yeah. So everything on your piece of paper, you can use it without identifying the source. Other things. So there will be one exercise today. Most likely it will be this year's problem. And remember what we're going to do next week? Next week is online. 不用在现场，it's pre-recorded. 好，这个部分呢，这个部分其实it is actually a very good example of this separable function method. I didn't recognize it. It's an adiabatic process in thermodynamics. 你们在general physics 有教过 adiabatic？
有。
都学会了。
我考得烂。
好，没关系。So maybe you want to take a look at these transparencies. Actually, the derivation about the adiabatic process is actually the same method as the separable function. Identical. Because here, I also separate here. Right? Also separate. I also separate the function and a variable on either side and take integration. So if you want further example how this separable function works, this is a very good example. Okay, very good example. We don't have time to cover it, so that's in gray background. So I don't cover it, but if you are interested, you can take a look. Next week, when we are online, we only halfway. Remember, we haven't solved the vertical speed. The vertical speed will be a different function, equation of motion, different ODE, actually quite similar, with a minus g. With a minus g, actually change the character of the whole equation. That's why it's fun to solve it separately from the horizontal speed. Okay, so next week I'll show you method 0, and method 1. Actually, method 1 is here, and method 2. Okay, method 2 is called integrating factor. Okay, so next the topic of next week. If the topic of this week, keyword decay equation, separable function, and next week integrating factor. Another ingenious method by mathematician. This mathematician is Leibniz. So this work is 400 years old. 400年前的工作，300 maybe. Method 2, integrating factor. That's the next week's course. Another keyword next week, homogeneous and inhomogeneous. It's very sounds very peculiar words. What is it? Just one more minute. Okay, I'll show you. Inhomogeneous and homogeneous. Sorry about playing around. Yeah, homogeneous version and the inhomogeneous version. Next week, I'm going to show you that with this kind of equation, we usually call it linear. And if the right-hand side, this is dy dx, this is y, then the right-hand side function, if this is equal to 0, we call it homogeneous. Okay, and that's the decay function. That's the decay equation. But now, the equation we are going to solve next week, has a minus g at the right-hand side. So then it is called inhomogeneous. So next week, the keyword, inhomogeneous and homogeneous. I will show you that the solution of an inhomogeneous equation depends hugely on homogeneous equation. They are quite related to each other. Okay, and this result is even more important than the integrating factor. So integrating factor I have to teach, but you don't have much chance to use it. But this separation between inhomogeneous equation and homogeneous equation and the relation of their solution are almost everywhere in physics world. Okay, so next week, remember this keyword, inhomogeneous and homogeneous. Okay, see you next week online. Give me any question if you have to send it to email to me. Okay, see you next week.